May not work. All right, so we'll go part one, part two, I guess. Okay, so this is part two. So anyway, so what I was showing you was that the air molecules that come along get caught up in the surface, and the video we watch tomorrow will make this make more sense. But at some point, they separate, okay? Now you want them to hang on to that surface. That's why you make it fuzzy. You want those points to hang on to the surface as long as possible. Because what happens is, when they separate early, this is called a wake zone. And you guys have been on a boat? Everybody been on a boat? So if you've been on a boat, you look behind the boat, there's a wake zone. That's what happens with anything going through air or water, but any fluid, there's a wake zone behind it. And the molecules back here are very turbid. They're very chaotic. What? Oh, okay. Okay. All right, see you. So this is very chaotic, where you have a lot of turbulence. And so this tends to be a low pressure zone, because you don't have as many compared to the front anyway. The front is laminar flow. And so on the front, the air molecules are coming in and hitting it and then bouncing off. But it's kind of giving you a united front. And so this is a high pressure zone. So if you have a high pressure and the direction of motion is this way, if you have high pressure on the front side, then this is going to cause this back yellow arrow. That's the arrow drag, the RA. This represents RA. So you're going to get more drag when you have a low pressure zone behind the ball and a high pressure zone in front of the ball. Okay, so now let's take it and let's go with a tennis ball. Well, a tennis ball is fuzzy, and those little air molecules hang on. They get caught up in the fuzz. Or if it's a golf ball, they get caught up in the divots there, or the little dimples in the golf ball, and they kind of curl around. And finally, they separate. But they hang on to like 120 degrees. This being, once again, this is the DOM, and so they hang around longer. You still have that high pressure up front, but you don't have as much. You don't have as much of a wake zone behind it. So the low pressure, you see, compare the two wake zones. The low pressure wake zone is less effective, and therefore this is less drag. So you want this for a tennis ball. When you first open up a tennis ball can, I always like that smell, right? Open a tennis ball can. And those tennis balls in there, then they're all fuzzy. Well, good for about a year, depending on what you play. But then eventually they lose their fuzz. At that point, if you play tennis, they don't go near as far. So you need to have that fuzz, or for golf ball, you need to have those dimples to make the golf ball or tennis ball. The fuzzier they are, the better. Okay. And they've done studies and all this stuff. And it's all because of that separation point, which is the surface phenomena, which we'll talk about more tomorrow. Okay, so those are the two new equation sheets. Now, for the time we have left, we got about 10 minutes. Let's do a little talking about this. This was where we were Friday. We had developed the free body, and on the same drawing, the head to tail method. Now, normally you do head to tail method first, and then you transfer that to free body, which we'll do. I'll show you that actually probably tomorrow, and it's also on the practice problems. Okay, so yeah, and I said I need to make an SHV this weekend, which I did not do, but there are soldering help videos. There will be some on the practice problems. But let's go ahead and look at number 8 right now. So we have that space, we have that rocket on 7, and then the space capsule from it is now moving at 40,000 miles an hour. It's not accelerating, so the rockets aren't firing, so there's no thrust. But first thing you do is you draw your dot here, represent the object. And now I will open up once again the chat and see, go ahead and let me know what other forces I should be putting on here. on this intergalactic. So this is the Milky Way. This is Andromeda. It's bigger. And here we are. We're right in between galaxies. So what other force should I put on here? Okay, so I see FP, a force of push. Now, in this case, the FP would actually be a force of thrust. But in order to have thrust, you had to have the engines firing. So the rockets aren't firing. So there is no thrust, therefore there is no push. What about MG? Is there gravity? Is there gravity between, now gravity is actually big G. Well, I'll take it back. It's actually, is there a force of gravity between galaxies? Is there a force of gravity between galaxies? The answer is yes. Gravity is infinite. It goes infinitely far. Now it drops off as the square of the distance between planets, but it is still there. So there's still gravity out there. And obviously the space capsule has mass. So we have mass, we have gravity. We should put down mg. What direction? This way, like we always do, mg. Could it be this way? Could it be this?
MG would MG even be like moving, or would it go in the direction of motion?
mg is in all directions. There is gravity, but it's not, okay, it's omnidirectional. And what that means is you can't put it on a free body diagram. You cannot put six-headed vectors on a free body diagram. You cannot put mg, even though you acknowledge there is some gravity and there is obviously mass, you can't put, there's no place to put it. If it was orbiting a planet, yes, I know, like the moon, right? The moon has an mg that's pointed towards the Earth because the Earth's acting on the moon. But if it's not one vector, one arrow, you can't put the force vector. So you can't put mg. I can't put thrust because there is no engines firing. I can't put air drag because there's no air. I can't put lift, there's no wings. And even if it did have wings, it still wouldn't work. There's nothing to lift off of. Someone asked this earlier. They said, wait a minute, you mean there's nothing in space? No, there is the occasional helium or hydrogen atom or a ion, or plasma, but there is no like molecules. Like, I'm not saying there's not occasional one, but it's for all intents and purposes, it's 99.999% a vacuum. So nothing really out there. There's no force of lift. Once again, we can't put any lift on. So you know what? That's it. Huh. Now, if you want to, and there's always somebody in class that wants to put a momentum vector on there because it does have momentum, but you cannot it's illegal to put a momentum vector on a free body diagram. Those are only for forces. Now, if you really want to do this, I will certainly accept that. If you want to say, okay, but there is a direction of motion, and that's 40,000 miles an hour, just to make you feel better, that's okay to do that. In other words, you're picking a direction. It could be any direction, but you're saying, okay, I'm going this way. Now, this 40,000 miles an hour is, I didn't just pull it out of the blue. That is the speed. That's around the speed of what Voyagers are going, Voyager 1 and 2, which are now past they're still in the Milky Way, of course, but they are past our solar system. They're out into the Kuiper belt. They're beyond our solar wind. So they've gone way past Pluto. They're past the heliopause. So, but they're moving at around 40,000 miles an hour. Now, when I was at JPL with Dane, our old student, we were walking down the spiral staircase, and then there's this big, huge tube of lights. It's like a bunch of tubes actually, and there's little light beams that come down it. And I said, "That's a cool art project." He goes, "Well," he said, "Mr. Ashley, it isn't an art project. That signals that we're getting information from probes that are all over the solar system." So that's cool. So you'd see a bunch of lights come out. That was something they got from a probe or say, because they're always exploring Mars and things like that in Europa. And so it's, oh yeah, he could recognize it from just the light beams. That's this probe. That's the Pluto probe. Okay. Then a little tiny trickle came down. And I said, whoa, what is that? He goes, oh, that's Voyager. So Voyager still gives us little bits and pieces of information, even though it's so far away. It takes it days to get to us, just because even at the speed of light. I don't want to lie to you. I think it's days now. I have to look it up, but it's beyond Pluto. So for the symbol equations, dash, dash. Okay, now, sorry for the interruption we had earlier, but we are now about caught up. We had second hours that hit the lead class, and they got to go to the board on number 9. The other hours, I gave them 9 as homework, but let me give you a hint on 9. So it'll be our homework, and you should, off to the left, is a real good idea as these things start to become more complicated. And in fact, on tests, I gave you this box. On the left, there's 4 forces here, so I'll give you a box like this. You'll see it on the practice problems. And it says, okay, first list the 4 forces involved here. So let's do that first. Let's get that done. A helium balloon is rising and accelerating at 80 degrees to the horizontal with the wind gusting horizontally from the left. And the snapshot's at 10 miles per hour. Now let's do the old chat room again, and let's list what you think is a force. Looking off the front of the page, that's your table of contents. What force? We have 2 new forces we haven't dealt with in here. So start running them off. What do you think they are? Force of lift, not in this case because there's no wings. You have to have wings. Balloons don't have wings. There is a force of wind, so I'll put F sub W. That's one of them. Okay, what else we got? Force of push. There's nothing pushing it. If it had a hole in it, it would have thrust, but there's no thrust. There's nobody pulling it or pushing it, so we don't have force of push. Mg, it does have a weight, so we can put Mg in there. There's 2 more. Air drag, yes, it's not going very fast. And I always have students say, whoa, you said the air drag doesn't really start until 30. But this is a balloon. This is a very big, well, I don't know, very big, but it's big compared to its movement. So yeah, there is drag. There's a lot of surface area. So R sub A, there is that. And finally, what do we have? Buoyancy, there it is. Capital B. Now, buoyancy, we'll spend 30 minutes on it probably, talking about all kinds of buoyancies later on this week. But there is a B sub A. There's 2 different buoyancies, buoyancy of air, buoyancy of water. And so this is buoyancy B sub A. So those are your 4 forces. Now I want you just to think about it, and then try and do it, and then try and come up with 2 equations for tomorrow. So that's your homework. To do 9 and then write, don't worry about 10, just 9, and then write the 2 equations. Okay, spend 5 minutes doing that. Okay, well, apologies for the my screw up on the daggone battery. I'll watch that from now on. But other than that, it went well. Okay, I would stop the sharing. I guess I will. You can't see me. So I'll stop recording. Now, anybody have so if you're watching this is part 2, assuming part 1 recorded. All right, so I'll stop.